Hello, welcome to your introduction of the mole. We are still in Unit 6, and this is the second part of our unit. We're going to start to count atoms. So you already know that atoms are very small. They're so small you can't see them with the naked eye. You can't see them with a basic microscope. So how are you going to even count them? I hope you'll think back to the aluminum foil lab. We were able to measure the thickness of the aluminum foil without actually measuring it with a measuring device. So this is how we're going to count up atoms as well. But you have to know a few steps along the way. So when it comes to dealing with bigger units, with larger numbers, we already have some common units that we use. 2 shoes are known as a pair. If you go to the store for 12 eggs, you usually buy them by the dozen, is 12. 12 times 12 is 144, so a dozen. You may not be as familiar with this one. It's called a gross. Paper. If you go to the store to buy a pack of paper, a single pack usually comes in 500 sheets. That's known as a ream of paper. And then finally, when it comes to a very large number, 6.02 times 10 to the 23rd particles, that is a mole. Mole is the SI unit for 6.02 times 10 to the 23rd particles. So here's a picture of our little mole down here. So how are we going to use this? Okay, we're going to use this as a conversion factor. 1 mole is 6.02 times 10 to the 23rd of anything. Now this anything can be, for our purposes, atoms, molecules, or formula units. We call this Avogadro's number. Here's a picture of Avogadro. You've seen him before. He's on the front of your packet that I gave you. It's a derived unit. If you were to write the number out, it is 602 trillion, or 602 sextillion. To give you an idea of exactly how big this number is, I've got a few examples for you here. Okay, M&Ms. If you had 1 mole of M&Ms, they would cover the continental U.S. to a depth of approximately 125 kilometers. If you had 1 mole of tiny grains of sand, now think about that. You can see a grain of sand macroscopically or with your naked eye. Atoms are so much smaller that they're not going to take up near as much space. But a mole of tiny grains of sand spread out evenly over the state of California, and you would have a layer as high as a 10-story building. So when it comes to things in our everyday lives that you can see, a mole is not a useful concept because it's just too many. It's too large. Here's a few more examples for you that you can read through if you'd like. There's the mole song. If you'd like to go to YouTube, you can plug this in and watch the mole song. It's a little dated. It was made in '88, I think. So those different units, we're going to use the term particles to include molecules, formula units, or atoms. But when do you use these units in chemistry? So if you have something that is covalently bonded, it's called a molecule. H2O, 2 nonmetals, they're covalently bonded. If it's ionically bonded, we call it a formula unit. It's FU for short, or for an abbreviation. And then if it's just an element, then it's referred to as atoms. If you want a generic term for all of these, you can simply call it a particle. All right, so now we are going to calculate molar mass, and I'm going to move my screen up here. And I'm going to run through a few of these with you. Okay, so you're going to need your periodic table handy, and we're going to calculate the mass of 1 mole of each of these different substances here on the screen. For elements like right here, we just have potassium. The molar mass is the same as the atomic mass. So you're going to look at your periodic table. You're going to go to potassium, and potassium has an atomic mass of 39.0983. So the rule for us is going to be we're going to go to 2 decimal places from here on out with these masses on your periodic table. If there's not 2 decimal places, for example, if you look at lead is number 82 in the periodic table, and lead has a molar mass of 207.2. Then just use the 1 decimal place. But we're going to round to 2 decimal places. So for potassium, it's 39.10 grams per every mole of potassium. Now, for compounds, we're going to sum or add up the masses of all the atoms in the compound. So for potassium chloride, potassium we determined has a mass of 39.10, and now you look at your periodic table, you find chlorine, it's going to be 35.45, and we're going to add these 2 together, and you're going to end up with a mass of 74.55 grams per mole. This is the molar mass. 1 mole of potassium chloride will have 74.55 grams of mass. This next example, we have copper sulfate. So again, you're going to sum up the mass of all the individual atoms. So we have 1 copper, and you look at your periodic table, copper has a molar mass of 63.55 grams for each copper atom. Sulfur is going to be 32.07. But now we get to our oxygen. Well, in this compound, I have 4 oxygens. So I have to do 4 times the mass of oxygen. Oxygen's 15.9994. I'm going to write that over here. And we're going to round that to 16. So from here on out, for oxygen, we're going to use 16. So I have a little side problem. 4 times 16 is 64. So now I'm going to add up these 3 numbers, these 3 masses, 63.55 plus 32.07. Plus I had a total of 64 for my oxygen. You should get 159.62 grams in every mole of copper sulfate. The last type of problem, you may be given the name and you have to write the formula. Just as a review, don't forget to check your charges. Calcium is a +2, chlorine's a -1. So this is CaCl2. So now, when we work this out, I'm going to lower my screen a little bit here. For you. For calcium, the mass is 40.07. For chlorine, now I have 2 chlorines, so it's going to be 2 times 35.45. And I need to go ahead and work that out. That's 70.90. So the 2 numbers that I'm going to add together are 40.07 plus 70.90. That's going to add up to 110.97 grams per mole. I'll move my little face over here. Grams per mole. So there you have it. So I'm going to work 1 or 2 practice problems with you from your packet. So if you will grab your packet that looks like this that I gave you. Okay, so hopefully now you have your mole packet that you all went home with. You've got your mole on here, you've got Avogadro. And here's a picture of one mole of different elements, as far as we have sulfur and copper, and then we have a few different compounds. You can see, or you already know, that atoms come in different sizes. We talked about atomic radius with the periodic table. As you move down the periodic table, the radius gets larger, with francium being a very large atom. And then as you go across, the radius gets a little smaller for each of the different periods. So considering atoms come in all different sizes, then a mole of either an element or a substance will occupy a different amount of space. It's going to be a different size per se. So if you want to flip over, at this point, this is what you should have in your notes if you don't already. We have gone over that 1 mole of anything is equal to 6.02 times 10 to the 23rd particles. Now, particles is the generic term. I've told you we can get more specific and talk about atoms. We could be talking about molecules if it's covalently bonded, or formula units is the correct term if it's ionically bonded. I will tell you, most of the time you're going to see atoms and molecules. Sometimes they don't use formula units correctly for the ionic bond. So what we just talked about was the molar mass, and 1 mole of anything will have a mass equal to the molar mass in grams. Now, where do you get this number, this molar mass? This comes from the periodic table. And from here on out, we're going to round to 2 decimal places. And you're going to look at the mass, the atomic mass, or the atomic weight of each element. So if you flip over, I'm going to do one of each example. So here you have iron nitrate. For your work, here's what you're going to have to do. You're going to show me, let me actually pause this. You're going to have to show me how you count up each atom in the compound. So over here for your work, you have iron. There's 1 iron. I'm going to put a 1 here. You don't have to do that. For nitrogen, we have 2 nitrogens. And then for oxygen, there are 6 oxygens. Now, you're going to go to your periodic table. You're going to find the mass for iron. You go to iron, you see the average atomic mass is 55.85 is what we're going to use as a rounded number. For nitrogen, it's 14.01, and for oxygen, we're going to round it to 16. So the next step would be to then get your total amounts. So I have 55.85 times 1, 14.01 times 2, which is 28.02, and then 16 times 6, which is 96. Then I'm going to add these all together. You get 179.87, and it's grams per mole. Now, what exactly do you have to do? You don't have to show me this step. You do have to do this. You need to show me how many you have of each one, and then the molar mass for each one. Then you can take these numbers here and throw them in your calculator to get your final answer. So then you can work out the rest of these on the back side. One more step here. You have to figure out the formula. So for calcium phosphate, calcium is a +2, phosphate is a -3. You're going to work this out. I'm going to take just a second. I'm about to run out of time to work this, and then I'll come back. Okay, so I wrote the formula for calcium phosphate. Then you need to count up the atoms of each. There's 3 calciums, there's 2 phosphoruses, and there's 8 oxygens. You get your you get your molar mass.